Welcome back. Let's now go over something called Q-learning, which is a reinforcement learning technique, and I'm going to abbreviate reinforcement learning to be RL. In fact, let's first talk about RL in general. Don't forget to enroll in my free Udemy tutorial, Vehicle Suspension Control 4, PID Tuning with AI, TD3. You will get access to the code files and explanations in there. Also note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. Reinforcement learning is a branch of machine learning that teaches an algorithm to do something via the so-called carrot and stick method. The idea is that you have an entity called an agent. It can be anything, a robot, a vehicle. It completely depends on the context. And then an environment is what the agent influences. The agent performs some action on the environment. When it does so, it receives two signals back from the environment: observation and reward. Observation lets the agent know about the relevant changes that have taken place inside the environment due to that action, and then the reward tells the agent in some way if that change was desirable or not. It could, for instance, be in the form of plus or negative points. And then, over time, the agent learns which the best actions are. It learns which actions give it the most amount of positive rewards. We can unpack the agent box further in the following way. You have a policy that takes in observations. By the way, we can also view observations as environment states. Based on the states that a policy takes in, it outputs an action. Policy is an algorithm. It's a rule that outputs actions based on the received states. It can be a neural network or something else, something simpler perhaps. In order to teach a policy to give favorable actions based on the states of the environment it receives, we also need another block which contains an algorithm that trains the policy to take actions that increase rewards. It's an RL learning algorithm that takes in state, reward, and action signals and updates the policy accordingly. One thing that I want to mention is that if you were to compare the field of control systems to the one of reinforcement learning, then control systems is much more established, especially when you use linear approximations for your system. Reinforcement learning is quite a new field. There are no well-established rules. For example, designing a good reward function often comes down to trial and error. Nevertheless, RL is advancing rapidly and becoming more and more important. Before I move on to the topic of PID tuning with TD3, which is an advanced RL algorithm, I want to go through a simpler problem in which we will apply Q-learning, which is also an RL algorithm, to a small grid world in which we're going to have to find an optimal path from the starting cell to the goal cell. It will introduce certain concepts that will make explaining TD3 simpler later on. I'm going to take this example from Brian Douglas's tutorial on reinforcement learning. It's a very good tutorial that I also recommend you to watch. I've added the link to his tutorial in the description. In one of his videos, he used this grid world with a starting and an ending point. The goal was to find the optimal path that would take you from start to finish with the least amount of moves. You can see that Some of the squares are inaccessible. They're walls. When I saw this example, I wanted to apply what Brian was teaching, and I coded up this gridworld example in Python. The code and its explanation are located in the free tutorial on Udemy, in which you have to enroll. The link is in the description as well. However, before we do that, let's go over Q-learning and understand its main logic so that the code and its explanation would make more sense. In this 4x4 grid world, you have 16 squares, which are the 16 states that you can have. Each state has an n and an m coordinate. In every state, you can take 4 actions maximum. You can go down, right, up, or left. The only exception would be if you are next to walls. If you are in this square, then you can only go down or to the right. And if you are in this square, your only option is to go up. In order to make the RL algorithm understand which path towards the goal square is most optimal, we have to assign a value to each state action pair. Imagine that you're in a cell 1, 1, first row, first column. Let's denote that as a vector. Row comes first, and then you have the column. In this case, it's 1 and 1. In that state, you can take 4 possible actions: down, right, up, and left. The question now becomes, when your current position is 1, 1, which state action pair is most valuable? Is it more valuable to go up or down, or left or right? In other words, is the value of this state action pair greater, or is this one greater? These values here are simply numbers, and the greater the number, the more valuable that state action pair is. Logically thinking, this one, where you take the action to the right, in this particular cell 1 and 1 should be greater than going up from that cell, because when you go to the right, you get closer to your goal. For example, if this one is 8 and this one is 5, then that means that when you're in the cell 1, 1, then this is how you numerically indicate to the agent that from that cell it's more beneficial to go to the right compared to going up. Practically, it means that when you go to the right from that cell, you will reach the goal cell with less steps. The number that we use for giving a value to state action pairs is called a Q value or a Q number, and we denote it in this way. First you have the state vector, and then in general you would also have an action vector here. However, in this particular example, you can only take one action at once, so our action will be a scalar. You can either go up or down or left or right at once. If you had the possibility to, for instance, take up and right at the same time, then that would allow you to move diagonally, but in our case we cannot do that. So A will remain a scalar. The next step is to create a Q table which will tabulate all the possible state action pairs. In this Q table, you will have all the states here. Since you have 16 states, you will have 16 rows, and then here you will have 4 actions, so 4 columns. Each entry in this Q table contains a number, which is the Q value for each state action pair. And in total, we have 16 by 4 or 64 state action pairs, which means that we have 64 different Q values. To solve the grid world problem, we first need to learn which state action pairs are more valuable and which ones hold less value. As we learn these Q values, in the end, if your learning is done right, the learning process should converge. It means that at first we initiate all state action pairs with 0 Q values, then during the learning process I always give random actions to my agent whatever cell I'm in, and then I update the Q value of the state action pair that I ended up choosing. If I'm in state 1-1 and I choose to go down, then in the Q table I update the entry that has 1-1 here and then down is here, so I would update this Q value. In my code that you can see in the free Udemy tutorial, I run the loop that updates the Q values 10,000 times. And as I do that, ideally, as mentioned before, these Q values here should converge to some optimal values. It means that as you keep running the learning loop, the Q values change less and less. In other words, they approach some optimal values that I will denote with Q asterisk. And then, after learning, once we're done with the learning process, we are going to apply the learned Q table to guide our agent to the goal cell in the most optimum way. In other words, we will deploy the trained Q table, which will be our policy. After deployment, our agent will only use this box here. The other box is only for training. When you deploy your trained policy, in this particular example, the agent is going to choose its action according to this rule. In every cell that the agent finds itself in, let's say that it finds itself in this cell, it checks 4 possible Q star values for that state, and then it takes the biggest number. Let's say that if this entry has the biggest value, then it will choose this entry which corresponds to this action, which means that the agent being in this cell 02 will move down. Sometimes you can have a situation where 2 entries have equal values. In that case, it doesn't matter which action you choose. If these 2 numbers here were to be equal to each other, then you can either take down or right, and then it depends on how you wrote your program. You can, for instance, say that in that case, vertical movement is preferred. By following this policy, the agent will be guided to the goal cell in the least possible moves. So just to summarize, we first initialize all the Q values with 0, we then train the Q learning algorithm, and by doing that, we converge on the optimum Q values corresponding to every state action pair, and once we have this optimal Q table, we will deploy it where this will be our deployed policy, where for each state we choose the action that corresponds to the maximum optimal Q value. And now, in the next video, let's see more closely how this learning process happens. Thank you.